So yeah, hello everyone, I'm Mishan, and so I'll be presenting GaitForeMer, self-supervised pre-training of transformers via human motion forecasting for few-shot gait impairment severity estimation. So this paper deals with like Parkinson's disease and like how to diagnose it like in early stage. So, and this is mainly work from Stanford University and published in MICAI 2022. So overview of this talk, like, so I'll talk about first quickly motivation, then gate forward framework, results, and conclusion and discussion. So yeah, so first let's talk about Parkinson's disease, like it's some background about it. So it's a neurodegenerative disorder that, I mean, affects the movement, like, so the walking or like the actions of the person. And it is caused by like dopamine producing cells in brain. And symptoms are tremor, stiffness, and difficulty in walking and coordination, basically. So there is no cure yet, but like there are some medications which can mitigate these symptoms. So, and we can say like it affects like 0.57 people of like over age 45. So that's like millions of people all around the world. So to diagnose PD, so in short, I'm calling it PD instead of Parkinson's disease. So early diagnosis of PD, it involves like two kind of mainly diagnosis. One is like wearable sensors. So we can see here like, I mean, in this kind of diagnosis, a person wears like sensors in his hand, like to detect the tremor, then waist, ankle, knee and ankle. So, so yeah, so and these sensors could be like gyroscope or accelerometer. And so thing is that like these sensors are like kind of expensive to set up, and its sensor alignment, it is crucial. Like for example, I mean, we can't put the sensor randomly, and also like, I mean, there will be, I mean, a contact of the person. So I mean, it depends on the, I mean, it's not that hygiene as well. So, and so due to this reason, it's not scalable. And because of that, like there is another way of diagnose PD. It's from video. So from video itself, we can say a lot. Like for example, like a person's hand is tremoring or not. It's his walking pattern. So, and for this, like person just needs to walk like in front of camera, and specialist, like it will, I mean, he will, I mean, they will like look at the walking pattern, and they will let know like the, uh, I mean, if the person has severe PD or not. So main advantage is that it's, I mean, setup cost is very less, and there is no contact to person. And so due to this reason, it's very scalable. So it makes sense to, I mean, progress in video technology compared to wearable sensors. So PD from video, a diagnosis from video. So a person just need to walk like 10 meters in front of camera, and a specialist, like they look at the walking pattern, and based on this walking pattern, they, I mean, classify the, like the severity of the disease in like this scale, like movement disorders, Society Unified Parkinson's Disease Rating Scale. So it is generally like from 0 to 4, which 0 means none and 4 means severe. So yeah, so now question is like, can we automate this diagnosis? And so this paper mainly deals with this problem, like to automate the diagnosis of PD from video. And so here we can see like gait, or like person's walking pattern, it's very crucial. And we can leverage like many like computer vision techniques for specifically motion and gait analysis. So yeah, starting with the GaitForeMer framework. So I mean, to understand walking pattern, we got the idea like we need to understand like spatiotemporal understanding of video. So starting with the RGB video. So from the RGB video, they have like, they don't use the RGB video directly. They have like, they use skeleton of the video. So for that, they use like a ResNet 50 based like model, which is pre-trained from Vibe training method. So that they get like 3D skeletons. And so they provide these 3D skeletons to a pose encoder. So this pose encoder basically provides a vector for multiple joints within a skeleton. And in that way, we get like 1 to T like frame skeletons. So up to this point, there is no temporal component involved. Like all components were like frame independent. So yeah, then we feed these, pose encoded vectors through transformer encoder. So which looks at the which has like self-attention over the all these tokens. So it has like temporal understanding. And as the output, we get like the output tokens for each frame. And yeah, so we can, break this framework into like two parts. So this part handles like the spatial part, and this part handles the temporal part. So at the end, we have like a spatiotemporal vector here. And so that we can learn a linear layer on top of that to, classify the PD score like from 0 to 4. So it's simple like 4-way or 5-way classification. So, but problem is that like there are too many parameters to learn like from small amount of this kind of like walking data. So that's why like the authors, they propose like a, two-step training process. So one step is like self-supervised pre-training on like off the self action data set, which is large scale. And after, so we can learn like a lot of like, meaningful spatiotemporal features, which can be generalizable to to compute PD score. So, and second step is fine tuning for PD score. So for that, they have like a smaller data set. This data set like from, which is currently, I guess, like the only existing data set for this PD diagnosis. So yeah, so now putting all things together like on GaitForeMer training. So we know up to this part, like this part learns spatiotemporal features. And so for the to introduce like the self-supervised laws, they have like, so based on the T frames pose and like spatiotemporal tokens, they try to, decode those tokens and like, forecast the next frame's pose. So for example, the video is continuous. We'll have like multiple frames in, in the data set. So based on this T frames, they try to predict the T plus 1 frame. And so it's a simple, motion forecasting loss. So it is like simple, like reconstruction loss, or we can say L1 loss. So they just compare like this XT plus 1 to the ground truth XT plus 1, and you try to forecast the, pose of T plus 1 frame. And on top of that, they have like, we know this spatiotemporal token, and they learn a linear layer on top of that. And so for pre-training stage, they have like action classification, which is like 60 class classification from NTU dataset. And for classification, they use simple cross entropy loss. And for the second stage, like they have like 4-class classification, like for PD scores. So actually here I mentioned like they have like 5 classes from 0 to 4, but because of some implementation issues, because class 4 and 5 was very vague, so they merged them and like call it like 4-class classification instead of 5-class classification. Yeah, so training process, like, so we know like 2 steps, like first is self-supervised pre-training, in which they have like action classification task and motion forecasting task. And the second step, like they have fine tuning, in which they replace this action classification by score classification, and forecasting is still there. And so actually they mentioned this thing in their experimental section, actually, but it should be part of method. They have like an additional fine tuning as well. So where they just use score classification, like after these 2 steps, they use score classification, and which leads to 4% improvement. So now experiment setup. So they use like this MDS UP DRS dataset, which is, in which they have like 54 participants and their walking pattern. So, and they don't have any separate like train and test split. They use this kind of leave one out cross validation setting. And they have a large scale NTU dataset just for pre-training. And they have like around 56,000 video samples and 60 action classes. So these action classes are mainly like the control lab setup in indoor scenes. And for performance measures, they have like precision, recall, and F1 score. Yeah, so comparison with prior work, they have like a F1, I mean, yeah, so first row is their score. Like, so we can, I mean, deduce this performance measure only using F1 score only. So if we compare like their method with the prior work, they have like a significant improvement. So yeah, so then there is second protocol in which they have like a limited label data. I mean, limited data. So they, on where they use like 25% of data, 50% of data, or like up to 100%. So blue one is their method, and the orange one, it's the prior baseline. So we can see like this method, even using the 25% data, it outperforms the prior baseline, which with 100% data. So which seems impressive. And some ablation studies. So where they don't have any pre-trained data set, like for example, that NTU data set or pre-training stage. So they get around 60% F1 score. But when they include that pre-training with only action classification task, they get like 6% improvement. When they included like the motion forecasting branch, it leads to another 6% improvement. And finally, like using the both branches. And actually, I mentioned like the additional fine tuning. So this step is additional fine tuning, and it leads to additional 4% improvement. So in conclusion, we can say like it's a effective approach for like to diagnose like Parkinson's disease patients. It leverages self-supervised pre-training and like also on like action data set and also like motion forecasting loss. And it outperforms like prior baselines. Yeah, so here was the conclusion. And like, so here, I mean, I'll put like I'll mention some weaknesses. So in this table, like we have seen like when they compare with the prior work. So there is some problem with that. Like, so for example, the comparison is unfair because like, prior work, they do not have access to like additional large scale data sets. So that makes a lot of difference in like computer vision, tasks. So that's a kind of unfair. They don't have like, additional data set in prior work, and they are using that. And also in terms of like model capacity as well, they have like, uh, I mean, so the GaitForeMer, it is based on this STGCN, and they have like additional, we have seen like on top of the, they have like additional decoder and also like the vibe model as well, which also adds like additional data there. So yeah, then yeah, I am a bit of skeptical about, the reliability of the baseline, because here we can see like the baseline, like when they increase the data from 25% to 50%, it's actually decreased the results. So that's very weird. And like, I've never, observed this kind of thing in any semi-supervised work, like in action recognition or any other spatial temporal task. And yeah, so reliability is still questionable, like of baseline. And yeah, so there is another thing like this problem, it's not that difficult. Like we can see like the, yeah, just this, let's look at this, only this purple portions. So they have like 4 classes, and visually apparently it looks very different, right? Like, so, and so based on these visualization, this 76%, like that doesn't look impressive. Like this should have been like, more than like 80 or 90%, like because like gait recognition, like it already achieves like very fine-grained kind of, classification task. So, and yeah, so there is another problem with the protocol as well. Like instead of cross validation, they should have used like retrieval kind of problem where they, check the purity of the cluster or like try to match train and test split. So cross validation, it's very hard to say, like, because it's very small set. And yeah. So for future work, it could have been, I mean, one could improve by like using end-to-end model instead of like a vibe model. So we have seen like from RGB from RGB, they use vibe model to get skeletons, right? So that's a kind of information bottleneck. And uh, if one can make it like end-to-end, it could be like, it could perform better. Then second thing is that like appearance features, I mean, since they use skeleton only, they are kind of eliminating appearance features. But in the real world, I mean, the specialists like it do not explicitly look at the skeletons, right? Like it also, I mean, they also have access to the, I mean, they are also kind of biased to the appearance as well of person. Like for example, facial expression or like skin color change, etc. So, and yeah, I mean, instead of leveraging like action recognition as the self-supervised task, one could use like gait recognition as a self-supervised task, because like gait recognition is more fine-grained spatiotemporal problem compared to actions. Yeah, so that's all I have.